Hello, my name is Walter McGavran. I'm a senior in the MSCC program at Paul Lawrence Dunbar. I'll be presenting my project, a novel synthesis of N12-crown-4 methylphenothiazine, which I completed under the mentorship of Dr. Susan Odom in the Department of Chemistry at the University of Kentucky. Here I have a brief presentation overview. I will start with some background on energy and redox flow battery technology before going through an explanation of my synthesis objective, my methodology. Then I'll explain my results and the subsequent discussion that emerges from those results before going over some future work needed for the project. And then I will conclude with some acknowledgments and my works cited. So, over the past decade, the United States has become interested in scaling down energy production from fossil fuels due to climate change research and the data showing evidence that there are very probable long-term detriments to the planet should production continue at its current rate. Fortunately, there are several alternative energy sources, one of which is known as intermittent energy, which is an umbrella term that covers solar and wind energy. Now, intermittent energy has some compatibility issues with our current energy grid, notably the fact that intermittent energy, as its name implies, is an unreliable electricity source. It does not always produce energy. There's not always wind, and there's not always sunlight, which is a problem because our grid, which was constructed around 100 years ago, necessitates that there is energy always, electricity, I should say, always being produced from energy sources, or else the grid sustains some damage due to the fact that there are no electricity reservoirs within the grid structure. You would be surprised how little it has been changed since its inception, those at the beginning of the 20th century. Now, that is where electrochemical storage technology comes in, specifically redox-flow batteries, which are an emerging electrical chemistry storage technology. And though they are classified as a battery, they are quite different from the batteries that you know, which are most likely either lithium ion or lead acid batteries. They are different in that they are rechargeable and they are decoupled. Now, the rechargeability is important for manufacturing flexibility due to the fact that when the electrolytes need to be replaced, that can happen without having to replace the entire battery. The tanks can be emptied and refilled when necessary. And the decoupling is important because what that means is that charge and power are scalable independently of one another. So you would scale the charge by increasing the electrolyte tank, and you would scale the power by increasing the reactor core. And if you would like to see a rough diagram of what a redox flow battery actually is, there is one in the lower right-hand corner of the screen. And as you can see, there are two external tanks holding both the positive and negative electrolytes, the analyte and catholyte. And they pump liquid phase electrolytes in and out of a central core that generates power. And in this core, there is a membrane that moderates ion flow and electrical current. Now, modern redox flow batteries are commonly called aqueous, and that is because their electrolytes are made of vanadium and some acidic solvent. And vanadium is used because vanadium can exist in 4 different oxidative states, which is important for the mechanics of the redox flow battery. Now, unfortunately, vanadium is not a long-term viable solution due to its relative scarcity, as well as other demands for vanadium, which is why many researchers are looking more into non-aqueous redox flow batteries, which substitute the acidic solvent for an organic solvent, most commonly acetonitrile, and the vanadium for lithium salts and an organic species, which could be phenothiazines, anthraquinones, quinones, phenazines, various orders of organic molecules and their derivatives have been found to serve fairly well as these charged species in the redox flow batteries when they are paired with lithium salts, which leads to my goal. I am trying to implement an intuitive binding location for the lithium salts with the phenothiazine, which is one of the most dependable molecules that have been tested to work in redox flow batteries. And the reason for this is that should there be an intuitive binding spot for the lithium salts on the phenothiazine, you will see a increase in solubility, stability, and kinetics when running the actual redox flow battery. Now, some of the reasoning and rationale for this, in fact, for stability would be that when the lithium cation interacts with the oxygens within the crown ether, you have intermolecular forces that bind the lithium salts to the phenothiazines, which increases the stability, obviously, which in turn increases the longevity of the non-aqueous redox flow batteries, which has been one of the most prevalent issues, is the degrading of the electrolytes. Another benefit could be the increase in solubility due to the addition of the phenothiazine, which is important because if you consider each individual molecule having a certain charge capacity, and increasing the solubility means that you can increase the amount of molecules within the electrolyte cell, you are in effect increasing the amount of charge that can be held within the cell. This is important for viability on a large scale because while small-scale batteries are fine for research in labs, if they want to actually be implemented, we need a battery that can hold quite a bit of charge. And another benefit potentially of the crown ether addition are diffusion rates throughout, with the ions diffusing in and out of the membrane inside the central core. Now, my methodology was originally a 5-step synthesis, starting with glycerol, though that was cut down to what you are seeing here is a final synthesis of 4 steps. This starts with the commercially available sulketyl, which is essentially glycol that is glycerol that has been protected with a dual methyl group. And it starts with the tosylation of the hydroxy group of that sulketyl, which is then, and tosylation is a reaction mechanism that is fairly well understood, and the mechanism itself is well documented, and tosyl chloride being the leaving group that I am attaching to the sulketyl as one of the better leaving groups. And I then transition into my second step, which is an SN2 substitution into the phenothiazine, which it follows steps that are, follows a procedure that is already fairly well documented, the methylation of phenothiazine on the nitrogen spot. I simply adapted those procedures using a tosylate rather than a chloride or a bromide. And my final 2 steps were a deprotection of the diol and then cyclization. Cyclization being the final and most important step, obviously. Unfortunately, it is also the most difficult step for the synthesis route. This is because cyclization is entropically disfavored. Reactions would rather make a chain, less energy is required. And so to combat this, I used lithium metal as a template, so to speak, to actually form the ring around. I also used butyl alcohol due to its higher solubility. And this reaction was adapted from the synthesis of a different crown ether, though using the same mechanics, more or less. So some of the results from the final synthesis step, unfortunately, it does not appear that the synthesis occurred in a large enough scale to be considered significant. You can see here an NMR spectrum showing that there is very little evidence that the reaction even started, and in fact, the reason that the reaction ended was due to gas chromatography offering no evidence that the reaction went to completion or even started. Now, why is this? I personally believe that a strong enough leaving group was not used. I used ethylene glycol dichloride. The proper step probably would have been to use ethylene glycol ditosylate because tosylate is a better leaving group. The sulfur can take more electrons on than the chlorine can. And due to the fact that it is entropically disfavored, a stronger leaving group would have most likely aided the synthesis. And I also believe that a larger scale ratio of the lithium metal was needed for the template method to be more effective. So unfortunately, a significant amount of product was not yielded from this specific final step, though it is noted that the previous 3 steps were all very high yield, ranging from quantitative to around 74% for the diol deprotection, which was acid catalyzed. So there is an alternate route of synthesis available for this molecule, as with most molecules. Though this synthesis is not economically viable and would only be able to be used in a laboratory setting, and it starts with the tosylation of methyl crown ether and then a simple addition onto a phenothiazine following the same steps as methylation of phenothiazine, which is, as previously stated, already reported on. Now, the success of this synthesis is less important to the overall project due to the fact that it is only for laboratory settings and for gathering data, though it should be noted that the tosylation and the addition reaction are relatively high yield, and so for those settings, it is a viable method. And so future directions for the project obviously will be a resynthesis, rerun of the synthesis route, solubility, conductivity, crystallography, quantitative analysis, cyclic voltammetry analysis in the presence of different lithium salts. There are many different types of lithium salts, as well as the synthesis and subsequent characterization of the radical cation versions. These radical cations are important because they're the ones that actually hold a charge most effectively, and if a stable version can be found, they function much more optimally than the neutral compound. And so I would like to acknowledge, as this presentation ends, Dr. Susan Odom, Giorgio Baggi, who was the postdoc that worked with me for the first half of this project, and the rest of the Odom lab. I would also like to give a shout out to MSCC and Ms. Karen Young for providing me with these opportunities, as well as the Kentucky Young Researchers Program and my friends and family. Here are my works cited, and normally, given a live audience, I would open the floor to questions, but unfortunately it appears that that will not be occurring. Thank you.